All right. Good morning, class, or afternoon, or evening, depends on what time you're watching this video. So this is a retake on the lecture done last weekend, primarily because I didn't have the best tool to, make some drawings. I just did a Google Meet annotation, so it wasn't as sensitive as I'd like it to be in writing. So now I realize Canva is a better tool. So good job, Canva. Now, um, this is also a clarification on a lot of the things I kind of made a mistake on last weekend. So this is a more smooth discussion, I hope. Okay, so here we go. So for this problem, we're asked to do method of joints and method of sections to analyze what are the forces in members BC, member CE, so CE, EF, EF, and CF. So these four members, we want to know if they're in tension or in compression, right? Also, we want to know what is the magnitude of these forces. Practically, that's what it is. So the way to go about that first is to solve your, oh, that's too big. Stick to this one. Okay, AY, your forces, reactions. Okay, AX, and then you have dy. You have to first solve for your reactions, just like any other um, typical problem we have in terms of equilibrium. We already know about this. All right. Now, if we try to sum up forces horizontal, okay, we see that all the forces going to the right are AX, sorry, AX, and then going to the right also is 80 kilonewtons equal to 0. Now, when you solve for AX, becomes negative 80 kilonewtons. So what does this negative sign mean again? Means that our first assumption for the direction of our force AX is opposite. So it means instead of going to the right, AX should be going to the oops, left. That, which makes sense, right? Because your force, your applied force is 80 going to the right. So to balance out your structure, you have a opposite and equal reaction in AX going to the left. So that makes sense, right? So make sure that when you change the arrow direction, you also change the unit, the sign of your magnitude. So now it just becomes positive 80 kilonewtons. All right. Don't change the direction as well, and then forgetting to change this sign. That you have an error with it. Next, summation versus vertical. Okay, so summation versus vertical, you see that AY plus DY is equal to force going down is 50 kilonewton. So when you solve for, in this case, AY, that's 50 minus DY, right? Now you want to know, okay, so how do I solve for DY? You, because you can't practically solve this yet, DY is an unknown. You have to sum up moments at A is equal to 0. Now, how do you go about that? Let me move here a bit. Summation moments at A equal to 0. Now, what does that A about this? At that point, you look at all the forces that makes the whole structure rotate, either clockwise or counterclockwise. So in this case, 80 kilonewtons is creating a clockwise motion, right? So this arrow is going that way. It will make your structure rotate. Also your 50. So 80 times 0.75 plus 50 times 2. Oops, that doesn't look like it. 2 times 2. Well, still better than last weekend. I'd rather show you these writings than compared to the other video. And finally, dy times going counterclockwise. That's times 3. See? Okay, times 3. There we go. I just have to erase that real quick. So it's not as sensitive. I don't have an Apple tablet. So, but that's fine. Does the job. Now, dy. What is dy? dy is 80 times 0.75 plus 50. Oh, that looks like a 3. Sorry. Plus 50. So I just need to write slowly. That's the trick. Okay. dy, in this case, if you solve that, you'll have 53.33. Okay. So when you get back here, oops, in your ay equation, you will have ay is equal to 50 minus, I think that's 80, minus 53.33. Okay, now ay is negative 3.33. Again, what happened here is we made the wrong assumption, which is not bad. It's okay, at least we know. Whoops. So that means this has to be going down. Now you ask yourself, does that make sense? And the answer is, of course. Look at that. The force, if you rotate about the axis, if you rotate about that axis over there, what are the forces that will create a clockwise motion? It's 80. 80 is going clockwise, counterclockwise. Now, if you try 80 times 0.75, that's still greater than 50 times 1. So with that, we need to have another counterclockwise uh, force that will create the rotation of a counterclockwise, or for you to balance your system. Okay, so we haven't really started on the solution yet, or for the method of joints, but this is crucial. You need to get this right, because if you don't, just like in last weekend's presentation, I made a mistake. So yeah, the mistake cascaded on to my solving of the joint forces. All right, let's get to it. Now, for method joints, you have no choice. You have to really start at the um, node that has a known force system. So in this case, we could start at A. So at A, you will have this kind of drawing over here. illustration, which I know you have already seen in online sources, which is where I got this from. So you have 30.33 kilonewtons going down, and you have an 80 kilonewtons going to the left. Oops, that looks like an 86. Let me try that again. All right. Now, with I'd like to establish a convention. So forces going away from a node, we call that a tension. And forces going towards a node, we call that a compression, right? So it's common practice that we start our solutions or assumptions as tension, right? It's just like earlier, the equation will just correct itself, and then we'll just have to reverse the um, the sign or the direction of the arrow. Okay, so for node A or joint A, joint A has two members AB and members AE. So these two have forces. Now to go and solve about those figures, we just need to do forces of summation of forces horizontal and summation of forces vertical. So summation forces of horizontal equals to 0. What we have is going to the right, that's AE, is equal to going to the left, 80. So that's it. That's our force AE. We could call this F, force AE and force AB. Okay, so that's 80 kilonewtons. Now summation forces of for vertical axis. Oh wait, actually not yet. Oops. So if you notice, AE has another force going to the right. Almost forgot about. That's FAB um, on the X direction, right? So it has, recall that we have an X direction and a Y direction for this force node, for this force member. So we account for that here. It's FAB X, FAB Y, right? Then we equate that to 80. Now, so can we solve this already? Not yet, because FABX, you need an FAB component force to solve it. So we need another equation. The other equation, we use summation of forces y. Just does not work. You need to really lift your pen up. All right, so slow here. Okay, so for summation of forces y, it's pretty simple because you only have one force going up, and that is FABY equal to force going down is 3.33. Now, what is FABY? In that case, we need a angle. So we need a angle, right? So angle theta, what is angle theta? So angle theta, we know from our figure that a distance of an opposite of 0.75 and an adjacent of um, 1. So that we will use tangent is equal to opposite is 0.75 and then we have 1. Now theta is equal to sorry, tan tan 0.75. That gives us um, oh, what is the angle? Let me quickly solve that first. So let me grab my calculator. Arctan 0.75, that's 36. So that is 36.87. Okay, that's 36.87. So when you're trying to solve for your FAB, you only need to use that angle. So F, oopsie, F um, A, B. Okay, is equal. Let me do the tangent version of that. Tangent 36. Oopsie, why does it not write that? Tangent 36.87 is equal to opposite. The opposite is FAB. Wait, we could choose not to use tangent because we're trying to solve for the hypotenuse in this case. So we just use um, sine. Sine 36.87. And then the opposite for that is FABY. I don't know what's happening. And your hypotenuse is FAB. Now you can solve FAB opposite over hypotenuse by solving FABY divided by sine 36.87. Okay, so with that, we will see that if FAB, yeah, FAB is 3.33 divided by sine 36.7. So we will get 5.15. I'm sorry, what's going on? I feel like my tablet's lagging. 5.55. Ah, there we go. 5.55 kilonewtons. So that is our FAB. Okay. Now going back to, so what does that mean for FABX? FABX is equal to, you could use tangent or you could use cosine at this point. So we could use cosine 36.87. Perhaps it does not work well with small numbers. Let me try. I need to zoom in. Cosine, oh, there it is. That's why. 36, it has to be a big enough zoom in. for it to work. 36. So now the adjacent is FABY, FABX, sorry, over your FAB. Okay, so that gives us um, is equal to your um, 5.55 times cosine 36.87. There you go. Yeah, so the answer for that is 5.55 cosine 36.87 is equal to 4.44 kilonewtons. So that is your FABX, right? Still use that here. You can use that here. So that we can use that to solve for FAE. I have to zoom in. FAE is equal to 80 minus 4.44. So we will get 75, oopsie, 75.56 kilonewtons. That is our FAE. Sorry. Okay. So now that we have that, let's take note of these figures. So we all got positive numbers. That means all are actually correct assumptions of the force directions. So let me clear this up a bit so that we could write our answers. FAB. See, FAB is what was the answer for that again? That's 5.55. And then your FAE is 75.56. Okay, now let me erase everything. Okay, next, let's go to, right, let's go to the node where we could solve a lot of things. So that is B at node B. Let's go to node B. At B, we see that we have a force. So this is your B, right? Okay. So the same way that, oopsie, that's too big. It's B. Still way too big. Anyway, I'm not sure why the weight is too low. Oh, there it is. There. Okay. Yeah. The same way that A, we did the force diagram, we will also do that in B. Now for B, we have force AB. We already know this. its intention, that is equal to 5.55. 5.55. Now, new forces are showing that FBC, so earlier we have a force going to the right, which is BC, an unknown, and ABE, which is not an unknown. So too bad. But that's okay. We still need that. So we call this BC, and we call this BE. Okay. So practically now we just need um, to break down the FAB to its components, because the moment we do that, we have our forces vertical and forces horizontal, right? So, oops, it's too big again. Too, okay, there we go. So, okay, kind of want to minimize this color. So we kind of want to break this down into its components, which we already actually know from earlier. We solved this guy, FABX and FABY, to sum up our forces. Summation forces horizontal, that's equal to 0. So forces going to the right is equal to forces going to the left. So meaning FBC is equal to FABX, which essentially earlier we saw that FABX is 4 point 4.4, right? Remember the 4.4? So we could actually also solve that again by, using 5.55 cosine 36 point something, the 87, I think, 36.87 angle that we solved earlier. So this one, kilonewtons. That's the intention. Oh, there it is. I haven't erased that. So let me erase that. That's why it's hard to erase. It's smaller. Mhm. Okay, so that's easy. Next, summation. Oops, trying to zoom in. Summation forces vertical equal to 0. Now, if you look at the diagram, both forces are going down. So that cannot be. FAY minus FBE is equal to 0. Now, if you try to put FBE here, you will end up with a negative FAY, which means you also have negative, let's try to put a parenthesis on that because it's a variable. So FAY is actually sine, so that's 3.33. Now the problem here is that, it's a negative. So that means this is a compression. Oops, we had the wrong assumption. Okay, I'm not zooming on, zooming in and compression. So that means here in this area, FBE should be, okay, wait, just real quick. So here have to be arrow going up to have that 3.33. Okay, and then this one is 4.44. All right. All right, that's correct. Okay, so that's it. So great. We were able to solve one of them, one of the unknown variables here. The unknown variable, which being this one. So we got that out of the way. Next, let's do joint E because it's the only way for us to reach EF and EC. So let's do joint E. Perhaps we could do it down here. Oops. At, oops. It's really difficult doing a zoom same time. At joint E. There we go. So at joint E, there's pretty much a lot of players in. So we have, so here's gonna be your, it's gonna be your E. You have a compression force over here that we've solved earlier. That's 3.33. And then we have the unknown FCE. And then this one, we also assume as tension. It's F uh, EF, force EF. Now earlier, we solved FAE as, that's 75, that's 75.56. Okay, now, and as always, we will break down forces that are in diagonal direction or not on a cardinal direction to its components. So this is FCE X, FCE Y. Okay, so this shows us that FCE Y can be solved quickly by solving for your forces. I don't know what's going on. Solving for your forces vertical. Okay, so force going up is FCEY equal to going down 3.33. Now, is that the answer? Not yet, because FCEY is a component. We need to first solve for the actual force, FCE. So how do we do that? We use a FCEY is a kind of a force going up, and you remember that we have a angle here, so we need to use sine theta to get the relationship of FCEY and FCE. We'll use sine theta is equal to FCEY over FCE. So we solve for FCE. It's equal to the value of our FCEY divided by sine 36.87. So 3.33 divided by, we will get FCE value of 5. Okay, it's not Starting to lag. 5.50. I should really change the way I write my number fives. 5.55. Right? Okay, so you may get like, plus minus 0.02. That's okay. So we got that ready in kilonewtons. Now we could proceed in solving for, okay, it's not writing. The precision is a challenge. Next up, we need to get our force horizontal. Oh, so that's going to be for another video. So F CEX going to the right. Oh, wait. Summation forces x equal to 0. FCEX going to the right plus FEF also going to the right. Okay. And then going to the left, that's 75. Let me try that again. Okay. 75 point, I forgot. 56 or 55 was it? Is it 55? 56. 156. Okay. I messed it up. 75, 56. Okay. Now, can we solve FCEX? Of course. We already did. Or we have not. Sorry. We have not solved FCEX. FCEX is actually using the relationship with FCE and FCEX. We can use cosine. Okay. Oh yeah, that's my family. So you guys pretty know much about my life at this point, or at least the people of my life. Cosine theta is equal to FCEX over FCE. Okay, so we already have that. We're looking for FCEX. That's how we're gonna move. FCE, again, that was 5.55. We'll use that number. We'll use that, if I can write it. 5.55 times cosine. So what was that, like 36.87? That's what we solved earlier again. So 5.55 times cosine 36.87, we get 4.44. So these figures kind of like just coming back. So now that we have that figure, let's go back to our main equation. Okay, wait. There we go. Let's go back to our main equation. So FCX, we move that this side. So FEF is equal to 75 4.56 minus 4.44. We will have 71.12. 1211 really depends on how far you were um, rounding up your numbers. So that's 71.12. And it is positive. That means we have the right assumption of having it on tension. Okay, now let's so this one is 4 points sorry FCE. Well, we already solved that. 5.55. So this one is 71.12. All right, so yeah. Now we're down to our, oh no, got erased, 71.12. Maybe I have to write that. Okay, now, last but definitely not the least, so point E. So we have that single joint over there, and it will have forces, in this case, as force CE or CF, actually, we'll see, FCF, then we have a force EF, which we solved earlier, another force here, and then lastly, 50 kilonewtons going down. Right? So since we're looking for FCF, we'll just have to equate forces vertical, up and down. So in this case, FCF is 50 kilonewtons. All right, we now completed our method of joints, or at least the ones that the problem is looking for. Okay, so I write that here. Okay, so 50. So for method of sections, um, it's kind of a process because we want that in this area. So for method of sections, we want to cut this location, and by doing so, we will reveal the forces. Whoa, what would that happen? By doing that cut, it will reveal the forces of those members. So, which we assume to be tensions forces. Okay, so that's for method of section. So we'll try to do that. What's going on? So let's try to draw that sections. It's pretty easy because for this one, you'll have to, you can practically solve a lot of unknowns at the same time. So that, so if I could just remember the forces. um, so let me check my notes. Okay, there we go. So AH, this is AP. This one is early from earlier. Actually, this is force going down. Oh no! Oh no! So this is going down. That's might as well erase those, right? It's going there. It's going that way. That way. This one is 3.33. This is your force, BC, force CE, and force EF. So that's like hitting three birds with one stone. Okay, so the technique for sections is that you want to try to isolate, um, you make summation moments. That's the key difference between method of sections and method of joints. We can use now method summation of moments equal to zero. So the key here is just to find the right location to make your moment equations to minimize the number of unknowns, right? So for example, we want to create a moment about, say, E. At moment E, you don't need to look to solve for FCE and EF because they're concurrent to E, point E, node, joint E. So same goes with 80. 80 falls on the same line as the path, the line of path of A, right? Of E. So with this, we just need to consider two um, variables. So clockwise go to counterclockwise. So for clockwise, that's FBC. Oh, I forgot to write the distances. This is 1, this 0.75. Okay, so 2, 0. Okay. Now, when you try to create that FBC, you have to have in a moment arm. Forgot to write moment arm. FBC times 0.75, right? And then 3.33 multiplied by 1. So this gives us FBC 3.33 divided by 0.75. We get 4.44. Okay. So if you compare that to earlier, FBC is 4.44. See, you just get the same answer still. Next. Next is look for another one that could yield, you know, at least one more unknown. So we look at perhaps where does FBC and FCE meet, right? So they meet at this point over here, which is C. So we could actually do summation of forces, summation of moments at C. Even if it's not there, imaginary, it actually exists, right? That member over there, that point over there is already defined. So what we can use that so that now in this case, at that point, we will only solve for EF, and then we will also use AT, and we will also still use 3.33. Okay, so let's try to build the equation that looks like EF. So as always, clockwise, counterclockwise. What are the forces that are making it go um, clockwise, right? So um, clockwise motion. So this one, and that one is counterclockwise. That is counterclockwise, right? So we can build our equation now. Clockwise is 80 times 0.75. Then counterclockwise is your FEF times 0.75. And then, oops, wow, that's a huge zoom. And your 3.33, which is not just 1, but 2 meters away, right? That's 2. So plus 3.33 times 2. It just isn't really right and very fine. Let's do that again. Plus 3.33 times 2. What? Yeah, 2. Okay. Okay, so we can now solve for FEF. So we build your equation. So you can actually move the 3.33 to the other side. 80.75 minus 3.33 times 2 over 0.7. Okay, good luck with that. 0.75 FEF is equal to 80 times 0.75 minus 3.33 times 2 over 0.75. That is 71.12. And earlier, we solved just that. There it is, 7.12. Okay, and lastly, we are looking for FCE. How do we get FCE now? FCE, if you look at the whole system, it's only FCE that has a vertical component, right? And then, so to use the least variables, use the least inputs, you will just sum up forces y. What's going on? Summation forces y. So FCE y, so it's going up, is equal to the force that's going down, 3.33. So for us to solve FCEY, we can use the sign relationship. Again, that's FCEY over FCE. To solve FCE, you can solve FCEY 3.33 divided by sine, oopsie, 36.87. You will get 5.55. So did we get the right answer? Is it the same as earlier? FCE, where's FCE? There we are, 5.55. Okay, so there we have it, guys. We're now able to learn. So how do you go about F? How do you go about FCF in this case? Well, you could actually do another cut, perhaps using, well, this one, because you now just will only have two unknowns, that and this, that's two unknowns. Or you could actually do a cut like that, but that's practically moment of joints, right? So yeah, there you have it. I hope you guys have now, have a better understanding of how to use method of joints and method of sections.